So section P.6, complex numbers. First, I want to say imaginary numbers are not made up. They are a real thing. They are actual numbers. They just don't exist on the real number line that you know and love. You know, horizontal number line, you know, that you've seen for all of your math classes. Imagine that's the x-axis. The imaginary number system does not exist on this x-axis. It exists, let's just say, above it, almost in a higher dimension if you want to think of it. Straight lines are one-dimensional. That's from geometry, yes? Okay, that means numbers that fall on the number line are one-dimensional things. Complex numbers, well, imaginary numbers specifically, are two-dimensional numbers. And if you would like to have a YouTube video about that, I can post it to my Blackboard channel. I didn't make it. It's an awesome video, nice visuals and everything, really explaining what they are. But let's just get this off my chest. They are not made up. Cool? They're not made up. They're real numbers. Well, they're imaginary numbers, but they are a real thing. Okay? Okay, great. So what is a complex number? A complex number is any number that has both a real part, called the component, a real component, and an imaginary component. So in a complex number, the A would be the real number. The B would be the complex component. Like I said, they're two-dimensional. You can almost treat it as an x comma y in the imaginary plane. And that's why it's actually called standard form, A plus BI, because the real part has to come first. Just like in every coordinate pair on the, XY axis, X always comes first. So we always have to have the real part first. There, that's out of the way. So let's talk about some complex number arithmetic. Adding complex numbers, remarkably easy. You just combine your like terms. That's literally it. I is a number, but you can treat it as a variable when you're adding i's. Okay? So because we're adding, these parentheses really don't mean much to us. We just ignore them. They don't do anything for us except for get in the way. You just combine your like terms. In standard form, 7 and 4 makes 11. Negative 3 and positive 5 makes positive 2. So it's just 11 plus 2i. That's it. Don't make that difficult. It's that easy. Just combining like terms. Your real component is 11. Your imaginary component is 2. Easy peasy? Everybody cool with that? Nobody's saying anything. Okay. Just making sure. Cool. Well, subtraction is the same idea. It is just combining like terms, but like I said to you last week when we were doing, foiling and distributing and things like that, watch out for those negative signs. This is actually a negative sign that you would be, quote unquote, distributing to both of these objects. It's minus 8 and minus 3i. 2 minus I minus 8 minus 3i. Now, again, just combining your like terms. 2 minus 8 is negative 6, and negative 1i minus 3i, negative 4i. So I hope that adding and subtracting complex numbers is remarkably easy for everyone. Awesome. Unfortunately, I think, as is usually the case, multiplication and division not quite as simple as addition and subtraction. Before we go on to multiplication of any kind, I want to talk to you about the powers of I. So what is I numerically? Anybody know what I represents? There it is, the square root of negative 1. So I is literally the square root of negative 1. Now the square root of negative 1 has value, but our tiny human brains simply can't comprehend what that value means, so we give it a symbol, I. But it is a number, it does have value. What happens when you square a square root? Yeah, the radical goes away. They cancel each other, right? So, I squared then, can we agree that that would have been this? just, replacing the I with square root of negative 1. Comfortable with that? Well, check it out. They just cancel out and you're left with negative 1. So I squared literally equals negative 1. Let's be clear about this. I is not a negative number. I is the square root of negative 1. I squared is a negative number. Okay? So if I is just I, it's square root of negative 1, but we'll represent it with I, and I squared is negative 1, then what is I cubed? Well, exponent rules. Comfortable with that idea? I squared times I is I cubed? Like x squared times x being x cubed? Is that all right? Yes? Okay, a couple people nodding, all right. Well, I squared, we just said, is negative 1. So negative 1 times I is just negative I. I cubed, therefore, is negative I. And lastly, I to the 4th is I squared times I squared. But I squared is negative 1. Okay. And those 4 powers of I to the 1st, 2nd, 3rd, and 4th, represent the only 4 values that exponents of I can take on. It doesn't matter what the exponent is on the I, it is one of these 4 values. It's either I, negative 1, negative I, or 1. It has to be one of those. The reason why is because every time you have an I to the 4th, that's just a 1. For example, I to the 23rd. What multiple of 4 fits into 23? Not by division, just is smaller than 23. 20, yeah. So what I could say is that I to the 23rd is actually I to the 20th times I to the 3rd. But if you remember, power to a power means you multiply. Then instead of saying I to the 20th, you could say I to the 4th to the 5th. But every I to the 4th power is just a 1. So this literally says 1 to the 5th power, which is 1, times I cubed. And I cubed is negative I. Am I going to test you on that? No. But it is a really good thing to know, because when you're going to do multiplication or division, or even addition and subtraction, if you see a power of I, any exponents on your I's at all, the very first thing you should do is handle that. Don't keep exponents on I's. If you see any power on an I, you need to change it to one of these things. Then do the mathematics. Not a whole lot of people seemed like, yeah, that all makes sense when I was writing that. Anybody have questions for me about it? No? Yes, sir.
It's I to the 4th to the 5th.
Yes. I to the 4th to 5th.
Does it just cancel out?
Well, it's not that it cancels out. It's just that the I to the 4th is literally equal to 1. And 1 to the 5th power is just 1. So it didn't cancel. It just happens to be a bunch of 1s that don't do anything when you multiply them. So again, I could give you any large number, I to the 101st. That's the same thing as I, because 100 is a multiple of 4. That's not on your test. I just wanted you to know it in case you do come across powers of I in the homework, powers of I in the work, like this question, things like that. Complex numbers are technically a binomial. They're made up of 2 parts. A real part and an imaginary part. When you multiply binomials, what's that acronym that you all like to use for multiplication? If it said like x plus 2 times x plus 3? It's a 4-letter acronym, starts with an F. FOIL. Yeah, you see, FOIL is not a real thing. FOIL is an acronym. It's not an operation. It's technically just multiplication, but this is a binomial. So when you multiply two binomials, you will use the foiling process. I haven't used red yet. So we have 2 times 5, 2 times negative I. Then we have 3i times 5 and 3i times negative I. And because I drew it in red, it looks like a lobster claw. That first 2 times 5, 10. Then 2 times negative I, negative 2i. 3i times 5 is just 15i. And lastly, 3i times negative I is negative 3i squared. Before I combine any like terms, I'm going to deal with the fact that this thing has an exponent on it. What does, excuse me, what does I squared equal? Negative 1. So what this actually says right here is negative 3 times negative 1. So that term will become a positive 3. And now it's no different from the first question. Combine your like terms and you're finished. 10 and 3, negative 2 and 15. Ta-da. Not bad, right? Got any questions for me? Anything I can help with? Explain in a different way? It makes great YouTube content. Yeah. No. So methodology really, that's really something more like your algebra teachers would worry about to make sure you actually have those skills. But once you get up to a level like this, you just say, look, whatever. That's why I said as far as factoring is concerned, I don't care what method you use as long as you can do it. For this, I'm not really sure how to do it any differently, but no, method for me doesn't really matter all that much as long as you know what you're doing and you're getting accurate, correct answers. That's all that matters. Okay. Well, that saves the last type of arithmetic, and that would be division. But before we can talk about dividing complex numbers, we have to talk about the complex conjugate. More specifically, in general, just what a conjugate is. Oh, that's a scary thing you do in Spanish. That's conjugate. Now, I don't know if that has any relation to this or not, but it's the same word. It must have some kind of relationship. What are conjugate numbers, though, is the real question. Conjugate numbers are numbers that are binomial in nature, exactly the same values. One has a plus in the middle and one has a minus in the middle. That's it. And you've actually been dealing with these this year already. You've technically been dealing with them since Algebra 1. A plus B and A minus B represent conjugate values. All that changed was the symbol on the second part. What do you always get when you multiply A plus B and A minus B?
A squared minus B squared.
Yeah, you get the difference of two squares, A squared minus B squared. This is a pretty big deal when it comes to doing complex mathematics, no pun intended. I mean, literally mathematics with complex numbers. Because if you were to square the front number, which was already real, you get a real result. Now, the back part of a complex number is always the imaginary part. But I squared always gives you a real number. So when multiplying complex conjugates, A plus BI and A minus BI, you will end up with a real result only, no imaginary numbers. Because it squares the A and squares the BI. And then you just put a minus sign in between them. Every single time. Oh, by the way, in case you see it in the textbook, Z, a lot of mathematicians, upper level mathematicians, Z is the letter that we use to represent complex values. You know how you see the fancy R means real numbers? Okay. Fancy Z does not mean imaginaries, but when we write the complex numbers, we use lowercase z's. You'll get used to seeing them in the textbook. So let us do some complex, not difficult, but complex division. We don't like to keep imaginary numbers in our denominator, just like we don't like to keep radicals in our denominators, you know? We don't want imaginaries down there. Not to mention if I said, hey, put this number in standard form. Standard form, remember, is a plus bi. Well, the way this is written, I is not in the denominator of a fraction. That is. So it can't stay there. So what do? We remember that a plus b times a minus b is a squared minus b squared. If you multiply conjugates that are complex, you will have a real number result. So we multiply the top and bottom of this fraction by the complex conjugate 3 plus I. I'm going to show a lot more work than I need you to in the homework. That's just because I want to have good notes and good video for future students. Top of the fraction is going to give us a 2 times 3 plus I. Simple distribution is going to occur up there. And on the bottom, we obviously have 3 minus I times 3 plus I. But remember, multiplying conjugates is always going to give you difference of two squares. So you square the front, square the back, put a minus sign in between. In the numerator, we are just distributing a 2. And you know, just because I'm recording, you guys don't have to stop talking to me. Like you can it makes good videos. So you guys, you're welcome to talk. Not to mention, it really won't be able to hear much of you. It's a good microphone. It pretty much only picks up sound from me. Okay. The top, numerator, done. Bottom. 3 squared is 9 minus, and what's I squared again? Negative 1. Well, 9 minus negative 1 is the same thing as saying 9 plus 1. Which would give you 10. Now, even though we managed to get the I out of the denominator, this is still not finished because it is not written in standard form, a plus bi, where the real and imaginary components are separated from one another. So what we do is we treat this as two different fractions. It's the addition of two fractions that happen to have the same denominator. So it's 6/10 plus 2/10 times I. And then you just reduce your fractions, and you're finished. Dividing both of these by 2 gives us 3 over 5, and dividing both of these by 2 gives us 1 over 5. So it's 3/5 plus 1/5 I. That is in standard form. What do you think? What can I help you with? What can I re-explain? What can I explain in a different way? Anything. She has a question. Yeah. Oh. Yeah, I wouldn't reduce until you separate them also, because we got lucky this time. They both happen to be divisible. All three of these numbers were divisible by the same thing. But what if it was, I don't know, an 18 down there, right? 6 over 18 is 1/3, but 2 over 18 is 1/9. So you're going to want to separate your fractions first and then reduce. You okay with that idea? All right, well, check this out. If you're one of the people that has already purchased this graphing calculator, which, by the way, you don't have to have for this class, but if you get it, I will be teaching you how to use it throughout the year. This calculator can be used to check your answers. Because, look at that right above the decimal point. An I. This calculator knows how to do mathematics with I. Of course, it's blue, so you have to use the blue second button in order to make it work. But here we go. Turn her on. The green button here says alpha. This is a shortcut I'm about to teach you. Alpha which I apparently missed the button. No, it's there. Y equals. So if you press alpha y equals, it brings up the fraction shortcut menu. And the one that's already highlighted is numerator over denominator. You just press enter. That is a stacked fraction. Type a 2 up there, because that was what the original question was. Press the down arrow. And what was it? 3 minus I. 3 minus, and again, you press second decimal point. And then you can just hit enter. And it will show you if you were right or not. Pretty nice, huh? You know, a student taught me that. I didn't know it could do that until a couple of years ago. No, I wasn't cheating. It's just like saying, is using photomath cheating? Well, it depends on how you're using it. If you're using it to check your answers, it's not cheating. Unless it's my test, of course, then it's obviously cheating. But if you're using it to tell you what answers are without trying, yeah, now you're cheating. But I don't care if you cheat on your homework. You're only hurting yourself, not me. But you should be using any tool you need to make sure you know what you're doing. So everybody's cool with this now? Then let's do it again. Only this time, we don't have a single real number in our numerator. We have a complex number 5 plus I. The process doesn't change. If you have an I in the bottom of your fraction, you need to multiply the top and bottom by the complex conjugate. I'm trying to pick a good color for this one. The complex conjugate of 2 minus 3i is 2 plus 3i. Now again, I am going to be showing more work than I need you to show in your homework. That's because I want to have good notes. I wonder if that horrible noise that fan is making is going to show up on the video. And on the bottom, we are multiplying 2 minus 3i, 2 plus 3i. Multiplying complex conjugates is awesome because it always results in a real number. What's different about this one is in the numerator, we are going to have to multiply two complex conjugates, or excuse me, two complex numbers like we did on the front of the notes. Orange grab this time. Someone last period asked me, why are we going through the foiling process up here and not down here? And I said, well, technically we are, it's just a shortcut. When you go through this foiling process for conjugates, the two middle terms, one will be positive, one will be negative, and they'll always cancel each other out. So we are doing it, we're just getting there faster. Okay. In the numerator, what do we get? 10 plus 15i plus 2i plus 3i squared. And remember that 3i squared is actually you saying 3 times -1. In the denominator, square the front term, square the back term, put a minus sign in between. Now we're just going to combine our like terms. This is 10, and this is -3. So we have 10 minus 3 instead of saying 3i squared. So 7, 15i plus 2i is 17i. And what do I get in the denominator? Well, 2 squared is obviously 4. 3 squared is 9, I squared is I squared, but what is the value of I squared again? -1. So this actually says -9 times -1, which is going to give us 4 plus 9. And that's why our denominator is 13. Oops. And just like last time, you're not actually finished until you write this thing in standard form, which means separate the two fractions. This one is full of prime numbers. Absolutely nothing simplifies. It's not wrong to put that I on the top of the fraction, but it will never look like that on a test or in a book or anything like that. It's always written off to the side to make it very clear what the imaginary component was. The imaginary component is 17/13. A bunch of ugly numbers. Look at all those primes. Do you think you can multiply and divide complex numbers? Well, we can pull that off. Fantastic. Awesome. Then, the last thing we're going to do is we are going to solve quadratics that have, a quadratic, that has complex solutions. And then I want to show you something nerdy. The go-to method for solving quadratics should always be factoring. However, there are no two numbers that multiply to 1 that add to 1 in the real number system. But technically, there are two numbers that multiply to 1 and add to 1. They just happen to be complex numbers. But because of that, we can't solve by factoring. We will have to solve by quadratic formula. What's a good color? I'll write the formula in red. Negative b plus or minus root b squared minus 4ac all over 2a. Now we'll just fill it out. A, b, and c are all 1. So negative 1 plus or minus square root of 1 squared minus 4 times 1 times 1 all over 2 times 1. Ruh-roh, a negative number underneath the radical. Can we all agree that this radical actually could have been written as the square root of negative 1 times 3? Does that work? Great. From here on out, your job is to treat the number negative 1 as a perfect square, something that you could take the square root of and pull out of the radical, because the square root of negative 1 is I. Like that. Technically, you should say root 3i, but it's weird because sometimes it looks like the I is in the radical, and trust me, you don't want to have to worry about what the square root of I is. It's some severely upper level stuff. So let's rewrite this solution set as negative 1 plus or minus I root 3 over 2. This is obviously a set of complex answers because I have a real part and an imaginary part. We're going to separate them into their fraction forms. Negative 1/2 plus or minus. Again, the I will never be written on the top of that imaginary component. So it's just root 3 over 2 I. This is two different answers. It's negative 1/2 plus root 3 over 2i, and it's negative 1/2 minus root 3 over 2i. Two different solutions. Scary hard? Just make sure that you're reducing your fractions if you can at the end. You can never take something that's inside and something that's outside and make them reduce each other. It doesn't work like that. So that concludes the lesson, but now I want to show you something neat. Okay, I think it's neat, because I'm a nerd. Over here, I have Desmos. Desmos to the rescue. There's our quadratic, x squared plus x plus 1. I'd like for you to see that its axis of symmetry is x equals negative 1/2. I feel like we just said negative 1/2 somewhere. Almost like it was part of the answer set. I wonder if that's a coincidence. I wonder if that's a coincidence. What I want to do, I want to take this parabola and I want to shift it down 3 units, which would give us x squared plus x minus 2. This quadratic does have solutions. It does cross the x-axis. Real solutions. x equals 1, and x equals negative 2. You don't need to write this. I'm just showing you something that I find neat. This does solve by factoring, but I'm going to pretend it doesn't, and I'm going to solve using the quadratic formula. Negative b plus or minus root b squared minus 4 times 1 times negative 2, so plus 4 times 2 is 8.
That's a 9.
That is now a 9. Because I goofed. I see what you're saying. There we go. 8. It's going to add to 9. Sorry. This gives me negative 1 plus or minus the square root of 9 over 2. But what is the square root of 9? It's 3. So what I actually have is negative 1 plus or minus 3 over 2. Let's write this as two different fractions. Negative 1/2 plus or minus 3 over 2. Now let's go back to Desmos. By the way, can we all agree that 3 over 2 is 1.5? Cool. Let's go back to Desmos. Here's x equals 1/2. The line x equals, or excuse me, negative 1/2. And here's our solutions. Tell me, how far away from negative 1/2 is the number positive 1? 1.5. You mean 3 over 2? And how far away from negative 1/2 is negative 2? 1.5. You mean 3.5, or 3/2, excuse me. You mean the axis of symmetry left this distance and right this distance. Find your solutions. The quadratic formula always shows you the axis of symmetry and says how far away from the axis of symmetry are the solutions. Did you ever know that? That's pretty neat. You know when I learned that? Like 3 years ago. A student said it to me. In Algebra 2. Regular. He says to me, oh, and I actually think the question we were working on was something like this. I think that was our solution set. And his kid goes, oh, so does that mean the axis of symmetry is at x equals negative 1 and the answers are root 3 away from it? And unfortunately, you can't see my face on the video, but I was like, it does mean that. I was astounded. I had never realized that before. But it's really cool. I don't know. I think it's really cool because I'm a big old nerd. Anyway, maybe one of you thought it was cool. I hope. That's it, though.